Hello everyone, welcome back. And in today's video we are going to see velocity and acceleration. Okay, so you can see here velocity and acceleration, how to construct velocity and acceleration for a given 4-bar chain. Okay, so let's see one example, then we will see how to construct velocity diagram and acceleration diagram for the given example. So the dimensions and configurations of a 4-bar mechanism are shown. P1A equal to 300 mm, P2B equal to 360 mm, AB equal to 360 mm, and P1 P2 equal to 600 mm. The angle A P1 P2 equal to 60 degree. The crank P1A has an angular velocity of 10 radians per second and angular acceleration of 30 radians per second square, both clockwise. Determine the angular velocity and angular acceleration of P2B and AB and the velocity and acceleration of joint B. So here is the space diagram for the given problem. So you can see here. So where P1, P2, both the ends are fixed. So this is fixed link, bottom one, and this is the crank. Okay, crank or input link. AB is the intermediate and BP2 is the output link. Okay, so here P1, P2 are the fixed points. So for this 4-bar mechanism, we are going to construct velocity and acceleration. Okay, so we are going to draw velocity and acceleration diagram, and in the last video we have seen how to construct velocity diagram for a 4-bar mechanism. Okay, the same procedure. Some key points you have to remember. The key points like first you have to check whether speed is given. Okay, so once the speed is given, next you have to check the direction of rotation, whether it is clockwise or anti-clockwise. So once you know these two values, two data, then you have to find the velocity of the rotating link. Okay, sometimes instead of speed they will directly give angular velocity. Okay, so whether speed is given or angular velocity is given, no problem, you can go for finding the velocity of the rotating link. Okay, so this is one, and you know how to find the velocity of the given link. This also we have seen. So from the speed you have to find the angular velocity omega. Okay, if speed is given, you can directly use omega equal to 2 pi n by 60 radians per second. Okay, and from this you have to use this formula, velocity equal to omega into length of the link. Okay, if omega is given directly, you can substitute the omega and the length of the input link. You will find what is the velocity of that particular link. Okay, next first write the given data for the given problem. So here you can see the angular velocity, it is given directly. So instead of speed they have given angular velocity 10 radians per second, and angular acceleration they have given, that is alpha 30 radians per second square, and the distance of the each link. Okay, so here you can see P1A, it is 300 mm, and A to B 360, B to P2 it is 360 mm, and the fixed link is 600 mm. So all the lengths are in mm. While solving you have to convert in terms of meter. Okay, so once you know all the given data values, find the velocity of A with respect to P1. So for the given link, okay, for the given 4-bar link, we are going to find the velocity at this point. Okay, so this is fixed, so velocity will not be there. So if you consider this input link A P1, this one is fixed, so velocity will be acting at this particular point. At the same time, this link is rotating clockwise direction. Okay, therefore the velocity will be acting perpendicular in this direction. Okay, this will be VA P1. That means velocity of A with respect to P1. Okay. So to find the velocity, we have to use the formula VAP1, or velocity of A equal to omega AP1 into length of the link. Length of the link is P1A, that is 300 mm. If you convert, you will get 0.3 meters. Okay. Now substitute here omega, already it is given here in the given data. You can see it is given omega equal to 10 radians per second. Directly you substitute here 10 and the length of the link 0.3. You will get velocity at point A. Okay, so once you know the velocity, you can start constructing the velocity diagram. Okay, so let us see how to construct the velocity diagram for the given 4 bar chain. Okay, so the first thing you have to notice is take the fixed points. Here the fixed point is P1 and P2. Okay, now take the fixed points and just mark a common point here and name this as vector P1 P2. Okay, now velocity of A is acting in downward direction at 3 meter per second, but while drawing the velocity diagram you have to use some scale. Okay, so here it is 3 meter per second. So to convert into centimeter, I am going to take 1 meter per second equal to 1 centimeter. So if 1 meter per second equal to 1 centimeter, therefore 3 meter per second equal to 3 centimeter. Okay, so from here place your ruler here at this point, slowly move towards this point. Okay, and from here you have to generate, place it here perpendicular to this link. Okay, it should be perpendicular, means it should be 90 degree here. Place it perpendicular and move towards this point. From here 3 centimeter, 1 2 3. Okay, now this is moving downwards. This is velocity of A. Okay, so P1 is the fixed point and the other end is A, so this will be A. Okay, so next you consider the link AB. Link AB, since this one is rotating clockwise, automatically the other link will try to move in anti-clockwise direction, and the velocity will be acting perpendicular. Perpendicular here means it will be perpendicular to this one. Okay, it will be acting upward direction. So velocity of B with respect to A, it will be acting in upward direction. So you fix point A, already it is fixed here. So from point A you have to draw a line perpendicular. So place your ruler here like this and just move towards this point and draw a line. Just extend a line, that's all. Okay, so this is VB. Next one, this one is fixed, so the velocity will be acting here, and when input rotating clockwise, the other link will be rotating anti-clockwise. Okay, when this is going to rotate anti-clockwise, this is going to rotate in clockwise direction. Therefore the velocity will be acting perpendicular in this direction. Okay, so perpendicular to this direction, place your ruler here perpendicular to this one and just move towards the point P2. Already the point P2 is here. Just move towards the point P2 and just connect it by a straight line. Now this represents the velocity B. Okay, so this represents velocity B, VB. Okay, and this one VA, VP, P1A, AB, and this is P2B. Okay, BP2, and this is VBA. and this is A P1. Okay. Now once you have completed the velocity diagram, you have to measure the vector quantity. Okay, measure the vector quantity. So I already measured, I will show. So you can see here. So by measurement you can see the velocity of VPB2 equal to 2.2 meter per second and VBA equal to 2.05 meter per second. And in the question they are asking the angular velocity. Okay, so we have directly find the angular velocity here. The angular velocity, the formula is omega p2b equal to velocity bp2 by length of the link. Substitute the values, you will get 6.1 radians per second clockwise. Okay. Similarly, angular velocity of the output link AB. Okay. Similarly, you use the formula omega velocity by length of the link. You will get 5.7 radians per second anti-clockwise direction. Okay. So up to this, your velocity diagram portion is over. So next one, you are supposed to calculate, or you are supposed to draw the acceleration part. Okay. So to find the acceleration part, few things you have to consider. You can see here, for drawing the acceleration diagram, you need two components. One is tangential, the other one is radial component. Tangential component will be perpendicular to the link and radial component will be parallel to the link. Okay. And this one you please note, if the angular acceleration is not given, okay, there will be no tangential component, only radial component will be there. Okay. So if the alpha is nothing but angular acceleration. Okay. If angular acceleration is given in the problem, then you have to find the tangential component AT. Okay. So this is tangential acceleration. Okay. A superscript T denotes tangential acceleration. So tangential acceleration equal to alpha into length of the link. Okay. Alpha is nothing but angular acceleration. Okay. So you can see here, I have already calculated few values to draw the acceleration diagram. First thing, for each and every link you have to calculate tangential and a radial. Okay. Here you can see the first link. If you take the first link, here this is angular velocity omega and angular acceleration alpha is given. You can see here angular acceleration alpha is 30 radians per second. So once you know this alpha, you have to find AT. AT is nothing but what? Tangential acceleration. Okay. So you can see here tangential acceleration AT equal to alpha AP1 for the input link, alpha AP1 into length of the link. So alpha is given directly from the example. It is 30 into length of the link. You will get 9 meter per second square. Okay. And this is one component. I told you two component will be there in the input link. One is tangential, the other one is radial component. So now we have seen tangential, the other one is radial component. You can see radial component here. Same input link, radial component AP1 equal to velocity square by length of the link. Substitute, you will get 30 meter per second square. Okay. This is for the input link. For the intermediate link, you will not have the tangential component. You will have only radial component. Okay. For these two links, you will have only radial component. You will not have tangential component. Okay. Whereas for the input link, since alpha is given, you will have tangential as well as radial component. So I told you tangential means perpendicular, it will be acting in this direction. Radial means it will be acting parallel to this link. Okay. So this link will have radial component and tangential component. This link will have only radial component. This link will have only radial component. So radial component values only we are finding here. You can see this is radial component acceleration of B with respect to A. Okay, so the formula is V square BA by length of the link. You will get 11.67. Similarly, radial component of acceleration B with respect to P2. Here you can see this is B with respect to P2. This radial component we have found, okay, by using this formula. So V square BP2, this is V square BP2 by P2B. So from this we will get 13.44. So now we get all the values. Okay, now we can start constructing the acceleration diagram. Okay, I will keep the values here so that it will be easy to draw the acceleration diagram. Okay, so I told you consider the first link. For the first link you will have two components. One is radial component, it will be acting parallel to this one, and tangential component will be perpendicular. So what I am going to do is I am going to assume the radial component as x a dash. Okay, from here I am assuming it as x a dash, and from here to this end I am going to consider it as p1x. Okay, for radial component I am going to consider p1x, and from here to here I am going to consider it as x a dash. Okay, so let's start drawing the acceleration diagram. So place your ruler here. Okay, so before that what you have to do, just fix the points. Okay, what points? So these are all fixed points. P1 and P2 are the fixed points, so we will fix the common point here. Let us fix the common point. So I'm going to fix here common point. So P dash comma P1 dash comma P2 dash. Okay, this is common point I am considering for the fixed link. Next, consider the link AP1. Consider the link AP1. First take the radial component. Radial component value is how much? Here you can see radial component value is 30 meter per second square. I am taking the notation as P1 dash x dash. Okay, the value is 30, so we are converting this meter per second square into centimeter. I am going to take 1:2 ratio. 1:2 means half of this one. Okay, that means I can take it as 15. Okay, so 15 I am going to consider the scale. Okay, so 1:2 ratio I am going to draw half of this one. Okay, so half of this one will be in terms of centimeter, it will come nearly 7.5 centimeter. Okay, so I am going to draw the radial component now. Place your ruler here. Place your ruler and slowly move towards this point. Okay, place it and slowly move towards this point. I told you the notations. This is P1x. Okay, 7.5. It will come near here. Okay. So this is P1x. This is a radial of the input link. Okay. Next, you take this one. This one is perpendicular. Okay, perpendicular, and the value we know. Here you can see the value is 9 meter per second. Half of 9 is 4.5. Okay, so nearly I am going to take half of this one, it will come nearly 2.25. Okay, place your ruler here and slowly move towards this point without changing their position. This is one. Okay, now this is, I told you the notation will be x a dash. So already P1x is given and this is x a dash. Okay, so this is radial component and this is tangential component for the input link. Now connect this link to get the acceleration link. Now I am connecting this one with this one. This is acceleration P1 A. Okay. Next, moving to the second one. Second is intermediate link. So intermediate link is radial component value 11. So half of this one I am going to consider it as 5. Okay. So approximate I am taking. So 5 means I am going to take 2.5. So what you have to do, place your ruler here parallel to this one and move towards the point here. 2.5. Okay, this is radial component of, so the notation is a dash y. So this is a dash y radial component. Okay, we don't know the tangential component. Since tangential components will be perpendicular, here we don't know, you keep as such, or if you want you can extend here. Simply you can extend from here tangential component. I am just simply extending this one. Okay, right. Next, move to the next one. Next one is output link. The radial component will be parallel. The value is 13. Half of this is 6.5. Okay, so half of 6.5 I am taking it as 3. So place your ruler here and move towards point P2. So move towards point P2. Don't change the position, place it and move towards this point P2. And from here, 1, 2. Okay. So the notation is P2 Z. You know the position here. This is P2 dash and this is Z dash. This is radial component. Radial component, and tangential will be perpendicular. Na? So from here you have to draw a perpendicular component like this. So this is perpendicular component. Now draw the acceleration links. Connect this one denotes what? B dash. Okay, this is B dash. Now connect this one with this one by a straight line. You will get P2 B dash, P2 B dash. One more link A B. So here B dash, here it is A dash. Connect by straight line. So this is the acceleration diagram. So now what you have to do to find the angular acceleration, measure these values. What is this? This is acceleration B. Okay, and this is acceleration, this one is P1 A dash. Okay, here you can see this is acceleration P1 A and this is acceleration A dash B dash. Okay, and this is acceleration P2 B dash. Okay, now measure all these values and substitute, and I have already substituted. I will just show. So you can see here by measurement, this is A B P2. Okay, here you can see, I will show it. A B, acceleration A B P2. This is acceleration A B P2 by measurement. You can see it is 29.6 meter per second square. Okay, similarly Y B dash. What is Y B dash here? Y B dash. This is radial, means this is tangential component. Why we are going for tangential component? For angular acceleration, the formula is A T by corresponding link A dash B dash. This is length of the link. Okay, so angular acceleration equal to tangential component. So you have to measure the tangential value, substitute here with the length of the link. You will get what is the angular acceleration. Okay, similarly Z B dash. Z B dash is nothing but what? Z here and B dash. This is tangential component. This is radial. and this is tangential. Now again you measure this tangential component, so we find that zb dash equal to 26.6 meter per second square. Now for this one you have to, that is intermediate link, P2P is nothing but this is input link, intermediate, this is output. Okay, this is P1, A, B and P2, these are all fixed. So they are asking the angular acceleration for AB and BP2. Okay, now BP2 angular acceleration equal to alpha, formula is AT by length of the link. AT is nothing but tangential, already we have calculated here, AT equal to 13.6. so convert this 13.6 into, so you will measure in terms of centimeter, that centimeter you convert into meter per second square. Okay, then substitute here, you can see this one, so 13.6 divided by length of the link, and this is for P2B. Okay, so you will get nearly 73.8 and 37.8. okay, so once you complete this up to this one, so your example is over now. So now you know how to construct, this one is velocity diagram and this is acceleration diagram. Okay, so still if you feel any doubt, you can comment in the comment section. Thank you very much. We will see next topic in another video. Same theory of machines, one more example on velocity and acceleration diagram. Okay, thank you very much.